This lesson is about electromagnetic waves. Can you give any one example for electromagnetic wave? Radio waves. Light is an electromagnetic wave. What we observe day to day life, only light is useful to us to observe other particles. Is it not other objects? Right? Sound wave is not an electromagnetic wave. Right? When the frequency is very high, they only come under the electromagnetic wave. So we are now going to see what is an electromagnetic wave, how they are produced, and what is a wide range of spectrum it has. Right? So next is electromagnetic. How the electromagnetic wave is produced. So in first lesson we have seen about the static charges. First lesson was done about the static charges. Second lesson, current electricity. Current electricity means it is a varying electric field. In third lesson what we have seen, when a current is flowing through the conductor, a magnetic field is produced. So here the current means it is a varying electric field. A flow of charge, it produces the varying electric field. Do you all accept this? Current na electron move aguna, the electric field eppadi irukum? It will be a varying electric field only, change aithe irukum. In the distance of electric field irundha, when the electron is moving to another point, the electric field changes. Again when the electron is moving to the other point, the electric field continuously is changing. So this change in the electric field only is producing the magnetic field. Right? Current carrying conductor produces the magnetic field. Do you all accept this? Right. So this change in the magnetic flux change produces the electric field, again induced EMF, you studied in fourth lesson. So here whenever there is a variation in the electric field, produces the varying magnetic field. Variation in the magnetic field, again it produces the induced EMF, which is the variation in the electric field. Again this variation in the electric field again produces the magnetic field. So this change goes on producing electric and magnetic field continuously, is it not? So there is a disturbance happening in electric and magnetic field. This disturbance, it travels in a perpendicular direction to both electric and magnetic field variation. This disturbance is called as a electromagnetic field. Got it? How the electromagnetic wave has been produced? The source for the electromagnetic wave is an accelerated charge. Electron moving, it is being accelerated. So the source for electromagnetic wave is an accelerated charge. Underline that point. Underline panniyach. Right? And this electromagnetic wave in a material medium, it is traveling in perpendicular direction to electric field and magnetic field. So this electromagnetic wave has a transverse nature. This electromagnetic wave, it has some properties in it and characters in it. So they have been listed. The electromagnetic wave, it is produced by the accelerated charges. Second, it propagates in perpendicular direction to both electric and magnetic field. And it travels with the velocity of light, and it could be found with the help of a formula C is equal to 1 by mu naught epsilon naught. Root of mu naught epsilon naught gives you the value of C, which is the velocity of light. Right? The energy of the electromagnetic wave is provided by both electric and magnetic. Electromagnetic wave energy is a totality of electric energy and magnetic energy. It does not need any material medium to travel. It can travel through the space also. Right? Then another point is, it is not deflected by electric and magnetic field, since it is not a charged wave. It is a chargeless wave, so it is not deflected by electric and magnetic field. These are some properties of electromagnetic wave. Important 5-mark question. Right? Then how can we produce the electromagnetic wave? Hertz was a person who produced, and that therefore this experiment has been called as a Hertz experiment. He produced the electromagnetic wave or generated the electromagnetic wave in his experiment. In his experiment, he took two plates, right? A capacitor, two plates means it is equivalent to capacitor, right? And he connected these two plates with a small sphere, and that spheres have been connected to the induction coil. and this induction coil has been provided with a very high potential. Now, what happens? The air will be here, is it not? When a very high potential has been provided to this induction coil, the air inside in the gap, they get ionized, and these air ions, when it moves and touches the two spheres, S1 and S2, what happens? A spark is produced. Right? When you touch two wires carrying a current, what happens? You can see a spark. So similarly, when I say one wire is the ion, another wire is the sphere, when it touches together, what happens? Produces the spark. That spark only is an electromagnetic wave. And the frequency of the electromagnetic wave produced here by the Hertz was, it is 5 into 10 power 7 Hertz. This was the frequency he produced. And with the help of different plates, we can find out the frequency of the electromagnetic wave produced. If I use a different plates and different induction coil if I use, I can find out the frequency of the electromagnetic wave produced with the help of a formula used equal to 1 by L, where L is the inductance of a coil, this inductor, and C is the capacitance of these two plates. Clear, children? Next is, what is electromagnetic spectrum? Spectrum means having a wide range of frequency. Electromagnetic wave, it has a wide range of frequency, right? And its frequency you can turn and see what all the spectrum it has. When the frequency is from 3 into 10 power 22 to 3 into 10 power 18 Hertz, then this is the frequency, and the corresponding wavelength is 10 power minus 14 to 10 power minus 10, then it should be called as a gamma rays. And producing an electromagnetic wave, when the frequency lies between 3 into 10 power 22 to 3 into 10 power 18 is, then I have to call that electromagnetic wave produced as gamma ray. If the frequency is lying between 3 into 10 power 18 to 1 into 10 power 16, then I have to call it as a X-ray, right? And you know what is the wavelength, corresponding wavelength you can find, right? I'll tell you how to find out the wavelength when you have a frequency band. So if the frequency is lying between 5 into 10 power 17 to 8 into 10 power 14 means, then it takes up a name ultraviolet rays. If the frequency is 8 into 10 power 14 to 4 into 10 power 14, then it is a visible. If the frequency is from 4 into 10 power 14 to 1 into 10 power 13, then it is an infrared radiation. 3 into 10 power 11 to 1 into 10 power 9 means it comes under microwave. And then 3 into 10 power 7 to 3 into 10 power 4 means it comes under radio frequency. So when the frequency is in this range, it should be called as gamma rays, X-rays. Right? Now, uses of electromagnetic wave. Radio waves we use in the communication system. It is used in the television, right? Telecommunication, in cell phone communication we are using, right? Second, microwaves are used in microwave oven, and it is also used in the radar. Radar communication system make use of this microwave. Last year you studied about radar, right? What is radar means what? Radio, right? Infrared rays, right? Infrared lamps are used in physiotherapy. When you go to the doctor, physiotherapist, they will have some red color lamp. That is the infrared rays. Then infrared photographs are used in weather forecasting. The pictures what we are getting in news for weather forecasting, it is picturized with the help of a infrared radiation. Infrared radiations are not absorbed by air, so it is used to take the photograph in thick frost and in the moist areas. Then it is used to study the molecular structure. These are the uses of infrared radiation. Next is visible light. This visible light only is used for us to view the object, right? If there is no visible light, we cannot see anything. That is a big use of it, right? Next is ultraviolet radiation. Have you seen in water cans? UV treated. UV treated, have you seen? So this ultraviolet radiation, first it is used in preservation of food items. Correct? Whatever we day-to-day life we see, Have you seen Tani Candle Patrikingla UV treated? And you can see in the some tinned foods. UV treated food. It is used to preserve the food items. Second, it is used in the forensic department. Fingerprints we are using the ultraviolet radiation. Then it is used to find out the forged documents. Progress reports we can find out with the help of ultraviolet radiation. It is used to find the structure of the atom, right? And here X-rays. What it is used for? To find out whether any disorder is there in the bone, right? Then it is used in to find out the crystal structure. You would have studied in chemistry. Bragg spectrometer. There we make use of the X-ray, right? X-ray is used to find out or to analyze the structure of an atom or a crystal. Then gamma rays. It is used in the treatment of cancer. So these are the uses of electromagnetic spectrum. Then coming on, what is the type of spectra? What is meant by spectra? Spectra, it has a wide range of frequencies, is it not? So whenever a white light falls on a prism, what happens? We can see 7 colors. That is spectrum. Spectrum, according to its production, it is of 2 types. One is an emission spectrum, other is an absorption spectrum. In emission spectrum also, again we have 3 categories. Whereas in absorption spectrum also we have again 3 categories. Right? When your signature changes to autograph, what is success? Right. Now, spectra is divided into 2 categories, 2 types. One is a emission spectra, then another is a absorption. Right? Again here, the emission spectrum is divided into 3 types. One is continuous. Right. Then coming on to absorption also, it is again without right. So it is continuous absorption spectrum, then so coming on to continuous absorption spectrum, which is forming the continuous absorption spectrum, and you will give that example. That's all that. These are the details you have to provide for each and every spectrum. The details are right? So when you will get a continuous emission spectrum, when a substance is heated, when a material is heated, it gives out all wavelengths. This forms the continuous emission spectrum. Example, substance heated up. Any material heated up gives you the continuous emission spectrum, and it will have continuously all the wavelengths. That is why it is called as a continuous emission spectrum. Coming on to line emission spectrum, this line emission spectrum is produced whenever you give an energy to an atom, single atom, it goes to the excited state and comes down again to the ground state. And while it is coming down, it emits out the radiation. That radiation only is given as a spectrum, and that will have a single wavelength. One wavelength in the line emission spectrum. Got it, children? This is how the line emission spectrum is formed. Right? And it will have only single wavelength. Coming on, example for the line emission spectrum, mercury vapor lamp and a sodium vapor lamp. Got it? How to write? Then coming on band emission spectrum, where you heat up a molecule. Molecule has 2 atoms, 2 or more atoms, that is why it is called as a molecule. So when this molecular substance is given an energy, it goes to the excited state. Come back to the ground state. Let me say I have CO2, let me see. C goes to the excited state on taking the energy, comes down giving one wavelength, lambda 1, let me see. O2 again goes to the excited state and comes down giving out another wavelength. Right? So it has a number of lines. So this is the formation of band emission spectrum, and this will have a number of wavelengths. Right? Who have to go? Hola. Liya, no liya. Right? So, while this band emission spectrum is viewed through the spectrometer, initially it will be bright sharp lines. Whereas as it goes, it becomes fader. Got it, children? This will be the view of the band emission spectrum. So over, next we will go to the absorption spectrum. Continuous absorption spectrum is formed by passing a white light through a green glass. What happens? All the wavelengths will be continuously absorbed, only green color will be given. So this continuously all the wavelengths have been absorbed, therefore it is called as a continuous absorption spectrum, only green color is. Right? Second, coming on to line absorption spectrum, when a white light from a carbon arc lamp is allowed to pass through some white light, let me say, it is allowed to pass through a sodium vapor. Sodium, what is the nature of sodium? What is the color of sodium? That yellow colors, two yellow lines are there. These two yellow lines alone will be absorbed. And the other wavelengths you can see there. So only line has been absorbed, two lines have been absorbed. It forms a line absorption spectrum. Then coming on to band absorption spectrum, when a white light, same white light, is allowed to pass through a diluted solution of a chlorophyll or the blood. Right? What happens? You will get a bright background with the dark bands. You will get a bright background and the dark bands you can see. This is only band absorption spectrum. Clear, children? Is there any doubt in it? No. So how it is produced? What is the type of wavelength it has? And an example you have to give for each and every spectrum. கையை அடுத்து பிளட் கொடுக்க வேண்டியதுதான். பிளட் இருக்குல்ல, இந்த பிளட்டை எடுத்து டைல்யூட் பண்ணிட்டு அதுல ஒயிட் லைட் பாஸ் பண்ணும்போது when we view through the spectrometer, right, or the radiation which comes out, it is allowed to fall on a photographic plate. There you will get a spectrum negative பாத்தியா, அதை டெவலப் பண்ணா உங்களுக்கு கிடைக்குமா picture, right? Clear? So when a light falls on the negative, what happens? You get a picture negative is affected. Similarly, you are passing a light. Light is an electromagnetic wave. This electromagnetic wave then falls on the negative. What happens? You will get a picture of a spectrum, right? When you go to the net, you can see what is the spectrum. When you see, you can download the picture there. அது பார்த்தீங்கன்னா எல்லா லேப்டாப் கொடுத்துட்டாங்களா? Next is a Fraunhofer line. Fraunhofer line is a natural example for the absorption spectrum. How it is formed? Fraunhofer lines. In sun, we get a white light from a sun. So sun has two layers. One is a photosphere. Inside, core is a photosphere, which is at the temperature of 14 million Kelvin. Whereas the next layer is a chromosphere, that is maintained at the temperature of 6000. We are not maintaining it, it is self-maintaining at the temperature of 6000 Kelvin. Right? So when a white light from the photosphere, it travels through the photosphere, chromosphere. Chromosphere has lot of gases in it, is it not? So these gases, it absorbs. White light is a composite of 7 colors. 7 colors irukuma. The 7 colors, when it travels through the chromosphere, this particular gases, it absorbs its own color. You know that for copper it is red color. For sodium it is yellow. So these gas particles, they absorb their own color wavelength, and remaining when it reaches the atmosphere. It will be only ella observed. There is no dark line. This is the Fraunhofer. Clear? Next one is a fluorescence and phosphorescence. Right? When an atom is excited, when a substance with an atom, it is excited to the higher energy level. What is excitation? Excite every hour. Excite hour. Excite the atom, when it is given something an extra energy, it gets excited. You will go to the higher energy state. You will stay there till? No. It's not a permanent state. You will come down immediately. When you come down, it gives out the radiation. This is what is happening. Right? When the radiation or the de-excitation is happening, the atom which is going to the excited state, when it comes down to the lower energy state, it gives out the radiation in the time less than 10 power minus 5 seconds. Then this phenomena is called as a fluorescence. The atom, when provided with an energy, goes to the excited state. Then again it comes back to the lower energy state. By immediately it comes down to the lower energy state by the time less than 10 power minus 5 seconds. Then it is called as a fluorescence. Example given is when ultraviolet radiation falls on a material, it gives out the radiation in the visible region. Right? Visible region immediately by the time 10 power minus 5 seconds, it is called as a fluorescence. Clear? Fluorescent lamp la pathirukingla potta odane eriyum. Tube light illa. Tube light maari konja neram padhu. So there it is a phosphorescence. Clear? So now what is phosphorescence? Delayed fluorescence is called as a phosphorescence. Right? Whenever you give an energy to an atom, it goes again, it gets excited, goes to the higher energy state. It will not come down immediately. It takes some time to come down. Then it is called as a phosphorescence. Right? And it is otherwise called as a delayed fluorescence. Right? What is the specification in it? When you stop the radiation also in phosphorescence, it will be emitting out the radiation. Some atom it will be there in the excited state for some time now. Even though you stop the incident radiation, the emission coming down, it will not stop. It continues until there is an atom in the excited state. Is that clear? Right. Next one is theories of. So fourth person have given 4 theories about light. One was a corpuscular theory, second one is a wave theory, third one is a electromagnetic theory, and fourth one is a quantum theory. What is corpuscular theory? That was given by Newton. Newton said the light is a particle called as a corpuscles. These particles are elastic particles. When they fall on certain substance, when there is a force of attraction between the corpuscle and the material which it forms, they attract, they refract. Right? When they fall on any substance, when repulsion takes place between the particle and the surface, then reflection takes place. Repulsion means it moves, right, in the same direction from where it came, is it not? So it produces reflection, right? So here, according to this theory, the velocity of light in a denser medium was given to be more when compared to the velocity of light in a rarer medium. That was a very big drawback in Newton's theory or corpuscular theory. So it has been discarded. Second person, Huygens came and he gave the wave theory. This person said light has a wave nature, and this wave, when it travels through the medium should have the ether, a particle called as a ether. The space is filled with the ether. That is not true, right? So that is one drawback. And this person said the light had a longitudinal nature. No, it had only the transverse nature, right? And that was proved by Fresnel and Foucault experiment. Last year we saw Foucault method, right? Fatima Foucault method in the 11th standard. We didn't study, but when you see the old book, you will have the Foucault method, right? So with the help of Foucault method, the light was found to have a transverse nature, right? But this person was not able to explain the photoelectric effect. Light undergoes reflection, refraction, interference, diffraction, polarization and photoelectric effect is there, which the light undergoes. This wave theory was not able to explain the photoelectric effect. So, rather than explain that theory is a failure, right? Third person, he came and he said light, that was a Maxwell. That person, and he came, he told that light had a, it was an electromagnetic wave. It does not need any material medium to travel. And he said it is just a electric and magnetic disturbance. Clear? Next, again this person was also not able to explain the photoelectric effect. So the fourth person, so his theory was also discarded. So fourth person, Planck, he came and told light has two natures, dual nature. One is wave nature, other is a particle nature. Right? The light is made up of light is a form of an energy. Is it not? This energy is made up of packets of energies. They are packets of energy. These packets of energy are called as a quanta or photon. Right? And each photon has an energy E is equal to h nu, where nu is the frequency of the electromagnetic radiation. And h is the Planck's constant, which takes up the value 6.626 into 10 power minus 34 units. Right? Whatever be the unit. Right? So this was the condition given by Planck. It had dual nature. Then, if it has a dual nature, when it acts as a particle and when it acts as a wave, when a frequency is high, when it has a more energy, it acts as a particle. When it has a very less energy, it acts as the wave. So it had dual nature. Got it, children? So next is when this light, when falls on any substance like gaseous material or a gaseous atom, what happens after falling on the substance? Scattered, traveled in different directions. This phenomena is called as a scattering. This phenomena, behind this phenomena, what is the main factor is, what is that happening behind this phenomena is, when a light falls on certain material, immediately it takes up the energy, goes to the excited state and again comes back to the lower energy state, giving out the radiation, is it not? This radiation only is travelling in different direction as a scattered radiation. This is a fact behind this scattering. And this is a fact which was responsible for a sky to be blue in color. Right? And Rayleigh was the next person who came and gave why the sky appears blue, and he has given a Rayleigh scattering law. According to Rayleigh scattering law, the amount of scattering, how much it is giving the energy in different directions, how much it is getting scattered when falls on a substance, as given by Raleigh's scattering law. According to him, the amount of scattering is inversely proportional to the whole power of the wavelength. It is inversely proportional to the whole power of the wavelength. Since blue is having a very less wavelength, red has a very high wavelength, is it not? That is why we are using that color in the rapid signals. Right? So blue has a very less wavelength. So it scatters more. It is inversely proportional, is it not? Since blue has a very less wavelength, it is scattering more. This is why the sky appears blue. Is that clear? So this is a very, very important question, why the sky appears blue. How you will answer? According to Raleigh's scattering law, listen to me. According to Raleigh's scattering law, the amount of scattering is inversely proportional to the fourth power of the wavelength. Since blue color having a less wavelength scatters more. That is why the sky is appearing blue. But during the sunset time, the sun is appearing red. Why it is happening so? It should be blue only, no? Why it is happening so? When the sun is close, the earth part is closest to the sun. Blue color can reach the surface of the earth. When the part of the earth is moving on the other side, the blue scatters in between itself, and red only has the ability to reach the other side to the observer. It only can travel, since it has a very long wavelength, it can travel a longer distance and reach the observer. And whereas the blue color, it gets scattered on the way itself and it cannot reach the longer distance. Right? That is why During the sunset, the sun is appearing red. Clear? So this is the reason why the sky appears blue. The very important remark. When you analyze this scattered radiation, this radiation will have the frequency as the same of incident frequency, and additional frequency is also seen. This phenomena is called as this effect is called as a Raman effect. For this only he has been awarded the Nobel Prize. Why the sky appeared blue? For this only he has been awarded the Nobel Prize. Right? So what is a Raman effect? When a white light or a monochromatic light falls on a substance, the emitted out, scattered out radiation has additional frequencies other than the incident frequency. நான் என்ன கொடுக்கறனோ அதுதான் வெளியில வரும். அது இல்லாம எக்ஸ்ட்ராவா வரதுனா ராமன் effect. Additional frequencies are being seen. Right? If the frequency of the radiation emitted, scattered radiation is less than the incident radiation, then a line formed is called as a Stokes line. If the scattered radiation has the frequency more than the incident frequency, then it forms a anti-Stokes line. Clear? Now we will explain with the help of a photon. Right? Photon theory, that is with the help of a quantum theory, we will explain what is the Raman effect. Let me say, all the atoms will be arranged in the ground state level. Am I clear? Right? So all the atoms normally will be in the ground level. Right? So let me say 0, 1, 2, third level. Now, when I give out the incident radiation of energy h nu naught, some energy I am giving. Incident energy of incident frequency nu naught, h nu naught is the energy. Incident energy is h nu naught. What happens? This atom, it absorbs the energy, goes to the excited state, and that level is not permanent, so it is called as the virtual level. Am I right? Virtual is false. Right? So it is not permanent. It goes to the virtual level, again comes down, giving out the radiation. Scattered frequency or the scattered energy is less than the incident energy. Scattered energy, if it is less than the incident energy, it forms the scattered frequency less than the incident frequency. It forms a Stokes line. Am I clear? Right? If the atom not from the ground state, it is starting from the first level or the second level, it takes up the energy h nu naught, goes to the virtual level, that is an excited state, comes down to the level, giving out the frequency greater than the incident frequency. It produces anti-Stokes line. If the atom from the ground state goes to the excited state, gives down, comes down, giving out the frequency equal to the incident frequency, then it forms a Rayleigh line. Clear, children? It forms a Rayleigh. Can you see there is a change in the frequency happening? So the change in the frequency happening between the incident frequency and the scattered frequency is called as there is a shift, Raman shift. It's called as a Raman shift, and it is represented as del nu is equal to mu naught incident frequency minus scattered frequency. This is positive for Stokes line and negative for anti-Stokes line. So this is also one of the very important 10-mark question. So what are the things you have to write? What is the Raman effect? When an energy is given to the material or a substance, it goes to the excited state and gets scattered. You will have a frequency of a scattered light. Additional frequencies you have, including the incident frequency. So this is called as a Raman effect. So you will explain with the quantum theory. Each photon of energy h nu naught, incident on each atom, goes to the excited state, comes down, giving out the radiation of frequency. That is a scattered frequency having the same frequency as that of an incident frequency. Rayleigh line is formed. When the frequency of the scattered radiation is less than the incident frequency, forms a More than the incident frequency, change in the frequency, Raman shift. Positive for Stokes line, negative for anti-Stokes. Clear? When Raman effect is right? What are the applications of Raman effect? It is used almost in all branches of science. It is used to differentiate, classify the molecular structures. Then it is used in the Raman spectroscopy is applied to the study of properties of metal, and it is used to analyze the chemical constitution or the combination of the material. Here children, these are some applications of Raman spectrum. Next is wavefront. What is a wavefront? Only one ray is coming from the sun? Only one ray is coming from the sun? No. Number of rays are coming, right? So these rays, number of rays are coming. Please listen. Number of rays are coming. Am I right? Now, the rays which are in phase, where they have a starting point to be the same and the ending point where I need to find out its ending point is the same. They all join. This is called it is called as a wavefront. Right? What is a wavefront? When you drop, an example given in your book is when you take a stone and drop on the surface of the water. What you will see? Ripples are formed. Where the ripples are formed, the disturbance of the stone is given to the particles of the water, and the water particles get disturbed. So this disturbance is travelling in the perpendicular direction to the stone. Is it not movement of the stone? So this disturbance, when the particles which receive the disturbance at the same time, they get excited at the same time. Is it not? All those particles only, they form a wavefront. They only form a ripple. For water it is a ripple, for light it is called as a wavefront. Clear? The particles which receive the disturbance at the same time only, they are going to give out the disturbance to the adjacent particle at the same time. Those particles which receive the disturbance at the same time, only they get excited at the same time forms the ripple, or that is called as a wavefront in terms of light. So next, what is a wavefront? It is the locus of all the points which are in the same state of vibration. All the particles jump, that is a state of vibration, is it not? State of the particle. So that is called as a wavefront. What is a wavefront? It is the locus of all the points which are at the same state of vibration. Jumping, all the particles jump at the same time. Coming down, all the particles comes down at the same time. Right? And you can define the wavefront in different way. A wavefront could be defined which envelops the particle which are at the same state of vibration. The particles which are at the same state of vibration is enveloped, means that is called as a wavefront. Then coming on, if I have a point source at a finite distance, the source is here, right? I am seeing from here, means I will get a spherical wavefront. If I am going to view the wavefront from a distance, from infinity, the wavefront will be plane, right? So let me say a point source is there. So it gives out the radiation in all directions. When I get the spherical wavefront, now when I go to the distant point, what happens? The radius increases. When I get a small part, from this very big radius, it appears to be a plane wavefront, right? That is what? A point source at infinite distance produces the plane wavefront. Actually, it is spherical wavefront. When we consider a small part from the spherical wavefront, seems to be a plane wavefront. Right? A linear source, it produces the cylindrical wavefront. Have you seen slits? Small slits. Have you seen a spectrometer? In spectrometer experiment, they have been provided the light through a small slit. What image you are seeing? You are seeing an image, cylindrical image, right? So a linear source gives out the cylindrical wavefront. Clear? Next, how to produce the wavefront, right? And then at what distance the shape of the wavefront, we can how to decide it. That is given by Huygens principle. Huygens principle, it is used to locate the next wavefront. First ripple has been formed now. Where the second ripple will be formed and what will be the shape of the secondary wavefront? It is given by Huygens principle. So according to Huygens principle, each point on the primary wavefront acts as the source for the secondary wavefront. I get a first ripple and each point on the first ripple will become the source for the secondary wavelets. From there only secondary wavelets will arise, is it not? So here in light, each point on the primary wavefront, that is the first ripple, acts as the source for the secondary wavelets. Right? The secondary wavefront, it envelops, it covers all the secondary wavelets. Right? If I draw the secondary wavefront, all the wavelets, secondary wavelets are covered, enveloped by the secondary wavefront. So this is the Huygens principle. Clear? So Huygens principle, it may come under 3-mark question. Huygens principle is used to determine or to locate the secondary wavefront. Second, it is used to analyze what should be the shape of the secondary wavefront. Clear? Now, how to develop a secondary wavefront? So with the help of Huygens principle, we are now going to develop the secondary wavefront. We are going to locate the secondary wavefront. Let me say I have a source and it produced the primary wavefront. That is the first ripple. Let me say PQ is the primary wavefront. ABC are the points on the primary wavefront. Now, the distance traveled at any instant of time t, I want to find out what is the secondary wavefront, where it has been located. The distance traveled by the secondary wavelets is equal to velocity into time taken. Am I right? Right? Taking this as radius, A as B as C as center, draw a circle. Now joining all the tangents, I will get the secondary wavefront. And now can you see what is the shape of the secondary wavefront? We have located where the secondary wavefront will be, and have you seen what is the shape of the wavefront? The same spherical shape. If it is a plane wavefront, let me say from infinite distance the source is located. Now let me say A, B, C are the points on the primary wavefront in a plane, right? So let me say xy something, PQ or xy. Taking CG as radius, A as center and draw a circle. B as center and draw a circle. C as center and draw a circle. By drawing all the tangents, I will get the secondary wavefront. So this is how we can develop a secondary wavefront and we can analyze what will be the shape of the secondary wavefront with the help of an Huygens principle. Right? Next, when a light or